All right. Any questions from so far in the course? Everything's clear? All right. So today I want to continue this discussion on dark energy, and then we'll end up very quickly focusing on vacuum energy and the sort of microscopic origin of vacuum energy. So if you recall at the end of last time, we sort of sketched how the scale factor could depend on time, depending on the value of W for the dark energy. And you're to explore that in more quantitative detail on this week's homework. Okay, so you may notice my plots here are not great. You may notice some slight little differences when you do it properly rather than just this loose sketch. But last time we talked about the scale factor versus time. Okay, and so if you have a matter-dominated universe in the past, okay, radiation all the way down at t equals 0, which I'm not showing. And then depending on the dark energy, W, it's going to transition at late times into some new behavior, which will depend on W. Okay, so the one that's of extra importance is a kind of grow like this, say W of -1, as we discussed. So it asymptotes towards an exponentially growing function, A of t. And then sort of loosely speaking, if you have, say, a W between -1/3 and -1, as we discussed last time, it's some power law. Fast enough, it's not drawn very well, but it is a power law whose second derivative is positive. So its acceleration this will also asymptote to a regime where A double dot is positive. Whilst this has A double dot negative, it's deceleration. And then finally, there's the curious scenario where W is more negative than -1, and it actually diverges at some finite time, which I called T end. Okay, so the universe would stretch out infinitely at a finite time. Okay. Now these curves, I've drawn them here, just a note for your homework. I've drawn them as though they sit exactly on top of each other and just asymptote and just diverge in that way. But to get that behavior, it depends a little bit on what you hold fixed. Okay, so on the homework, I'm going to say that today, so here's T naught, we're going to fix the percentages. We're going to say it's still 30 or 31% matter and 69% dark energy, 70% dark energy. And if you fix those percentages, as well as fixing H naught, the curves are not going to be quite as simple as I've drawn. Is that okay? Because if you fix H naught today, you're making a statement what A dot over A is today. So the derivative here, or A dot over A, well, A today is 1. So A dot you're demanding is a specific number. So these curves here have to conspire to have the right derivative at this point. So, okay, so you can imagine, for example, maybe the red curve is going to do something a little different so it has the right derivative here. But the late behavior is qualitatively this for sure. Does that make sense? We have to kind of monkey around a little bit with the relative percentages at early time in order to get the H naught today that we observe. Okay, so that's why if you do the homework, you'll see that this will maybe look a little different than I've drawn it. Okay? Like there might be some things going up and down a little bit here. Okay, just look out for that. All right. So we would like to know what is the universe, what value the universe has chose for W for this dark energy. Okay, so again, I sometimes put a little DE subscript here for dark energy. And so you can imagine the strategy is to go out and just measure A versus T. Okay, so ideally we measure A of T, and we just see which curve fits it best. And again, there are some parameters. You do not know a priori that omega matter is 0.3. Maybe you have to adjust it to 0.25 or 0.35 or something. There's a couple of fit parameters. But if you can map out a whole curve and you have only a small number of fit parameters, like W itself in particular, you can imagine maybe there's only one good W that does the job. Okay, so you can imagine there's some data, so on, and maybe it will fit one of these curves, or maybe it fits none of the curves. All right. So let's say something a little bit more about what you measure. Okay. It's all well and good to say I just measure A of t. Measuring A of t is very difficult because of the t. Okay, the A is actually straightforward. So let's talk about that for one moment. Then we'll come to the measuring t. Okay? So in other words, on these data points, we're very good at measuring the height. We're not so good at measuring where it is on this axis. So really, I should have error bars that go in both directions. Does that make sense? Right? This would be, you want to say, what was the scale factor at which that light was emitted? So you look at some distant object, like famously like distant supernovae, and they emit light. And so they did it when the scale factor was some value, say 0.5 or whatever it was, and it happened at some moment in the past at some time. Okay? And so we have to, by looking at that supernovae, we want to know both of those things. What was the scale factor and what was the time at which the light was emitted? And then we receive it today. Okay? So the scale factor is relatively easy because remember that's related to redshift. So we measure directly how red the light is. Okay, remember redshift is nothing fancy. It's just the wave, it's just this formula. Okay, lambda here is the wavelength of the light, the wavelength at emission, and then the wavelength at observation. That's the redshift. That's how red, okay? The redder the light is, so the further, the longer the wavelength is when you observe it, the bigger Z will be. Okay? And the wavelength is just stretching, as we've discussed before, with the universe. So these factors here are nothing other than 1 minus A at emission over A at observation, which is today A naught, A emission over A today. And we set A today, A naught as 1. So those factors you can just erase. I don't need to write A naught. So this is 1 minus A over A. And I can certainly write A emit if I want to say those words. But usually we don't write that subscript. It's understood that it's the A at which it was emitted. Okay, so we often just would write this as 1 minus A over A. Okay, so the thing that you directly measure is how red it is Z. Okay, and so when people produce these plots, this axis here is usually not written as A, but as Z. But it's extremely simple to convert from Z to A. It's just that formula, as simple as you like. Okay, so Z is this, or you can invert and write A as 1 over 1 plus Z. Okay, so that's just a very simple inversion, right? So I'll just leave it as A instead of writing Z, or it's up to you. So far, so good? Okay, so there's atoms over there, let's say hydrogen. You know the spectrum of hydrogen, but you measure the wavelengths are significantly longer than the standard wavelengths you get out of a hydrogen atom. And then from that measurement, you can just infer, you can infer the scale factor at which that light was emitted at, because it has to have stretched to that value that you observe. Is everyone cool with that? Okay, so that takes care of this. Now, the t-axis is actually very difficult, right? Because you want to say, oh, there was this supernovae that went off. I look at how red the light is, okay. But now I want to know when the supernovae went off. How do I know? I just see the light now. But did it go off 1 billion years ago? Was it 1.7 billion years ago? When did it happen? Okay. So the other thing that we measure, which is related to that, okay, so these are the two things we measure, is the flux of the light, flux F. Okay, so we collect the light, and just by knowing how red it is, that's one thing that tells you about the spectrum. but the flux is related to the energy, the amount of photons you're receiving. And I remind you specifically, it's the energy per unit time per unit area. Okay, so that's the flux that you receive. Okay, so you all agree that these are two things that you can measure. Nothing too fancy. Okay. So let's draw a little picture of that. So let's say here is, I don't know, say a supernova that goes off, and it's emitting light in all sorts of directions. And let's say we're over here somewhere, that's us. And the distance between them, we'll call that x. And then if you draw a big sphere around this, of radius x, you know the flux, which is energy per unit time per unit area, is then related to the flux that you measure here at x. The flux is related to the intrinsic luminosity or power output divided by the area, this blue sphere. Okay, so that's just 4 pi x squared. Okay, so luminosity, remember, is the power output. That's energy per unit time. And then I'm dividing by this area to get flux. So the luminosity you want to think of as an intrinsic property of the supernova. The supernova knows its own luminosity. That's not related to cosmology. Right, so it just outputs some power. And then we observe a flux. And the further we're away, the smaller our flux is. We're only going to receive a tiny percent. We have a little detector here. Here's our telescope. We're only going to receive a tiny percentage of that light if we're very far away. So you see the flux we're going to receive is very small because x squared is in the denominator. Okay. Now there's a couple of things we have to do to improve that formula. That formula is slightly naive. So the first thing we want to think about always is what's the physical distance between them, right? X is co-moving. That's actually easy. That won't be the confusing thing. X physical, right, is X, the co-moving X, times the scale factor. Okay? But we measure this stuff today, right? Light hits us today. And today we pick the convention that A is equal to 1. So that's not a problem, right? So this equals X because we received the light today. Okay, so that X that I wrote there is the physical distance. Is everyone okay with that? There's a...
The point was that it's backwards.
That's right. The supernova is happening backwards in time, but the conversion from the distance x, right? There is still this sphere around it, and the sphere is going to house all the energy output from this thing. So we still have this relation. There's a caveat to this coming in a second. But the physical distance, nevertheless, the conversion between x and physical distance is nothing because we pick A is equal to 1. I'm not saying it's happening today. I'm saying that we collect the light today. That's the statement, right? So I don't draw the sphere. You know, if you thought, well, maybe I should enter the A at which this occurred, but when it occurs, the light is all just hanging out there. It hasn't even got out here yet. We care about the size of the sphere today. Okay, because that tells you the physical distance to the supernova today. However, there's a couple of corrections to this formula that we do have to worry about, which is that this light, because the universe is expanding, the photons are losing energy. We talked about that before when we talked about the radiation era. Okay, so the energy of a photon is basically the energy of the photon at emission divided by the scale factor. Sorry, I didn't even write that correct. Times the scale factor at emission divided by the value you received today. Does that make sense? As the universe expands, right, by a lot, by a big factor, the energy drops. Okay, so the photons, if I draw these photons, here's this little photon, but later it's stretched out. Okay, and the stretching is just provided by A. So again, we write A emit, we just call A, and A naught is 1. And you could also write this, if you like, energy at emission divided by 1 plus Z. Okay, so again, the objects, so the key thing then is that these objects that are far away, the light was emitted when the universe had a small a, or equivalently they were at a big redshift. The energy you receive is especially small, is extra small than you would have guessed because of the expansion. Is that all right? This is the energy per photon. So this is one correction factor. And then there's a second correction factor, which was related to the rate at which you collect photons. Okay, so you have a detector and photons are bombarding it. Okay, and we care about, energy per photon per unit time. So now I'm talking about the per time or the rate. So you can imagine that as these photons are emitted, okay, and as the universe expands, not only are the wavelengths stretched, which is what this captures, so they have less energy, but you can imagine the distance between the photons gets bigger. Does that make sense? So that here's a supernova and the light's heading to you, and here's a pair of photons. They kind of go like this. Wavelength stretch, but the gap stretches. So that means the rate at which photons will hit your detector is also suppressed because there's a gap between them. So you hit, instead of so the energy per time is also suppressed. And it's by the exact same factor. Does that make sense? So the rate is also, instead of writing it out, the rate is proportional also to the scale factor, or 1 over 1 plus Z. Okay. So if I put all that in here, the true answer you could write as 1 plus Z squared. Accounting for expansion. That's the expansion factor, and this is just standard sort of optics, if you like, factor. Okay, so then the game is, if you know the intrinsic luminosity, so like these type 1a supernovae, you have an idea as to what the intrinsic luminosity is. Then by measuring the flux, if you see a flux and it's very, very small, you know the thing is very far away. And then there's a correction factor associated with expansion. Okay. So let's see. So the final thing, which maybe I'll just squeeze it in here. What we also need to do then is I want time. And I haven't written time on that formula anywhere. Okay. So for that, let's, well, maybe I can just put it here. Right, so intuitively, time, I should be able to take that x there and convert it to time. Right, we would normally just say, oh, if we're in flat space-time, x is just ct, right? The time it takes is just is proportional to x by a factor of c. Nothing fancy, right? Further away it is, the longer the time would have taken to get here. All right? But now we have this expanding universe, we have to be a little careful. So for light, they have a ds squared of 0. Okay, I'll put the c's back in maybe for this discussion. If we were in flat space, you would have this. Okay, I can write dy squared dz squared, but imagine light moving just in the x direction. Okay, so that would be the Minkowski metric, right? And then setting light to 0, having a space-time interval of 0, you see it just says that dx is c dt. It's the usual statement that light propagates at speed c. And that's all true in curved space-time, except remember for the FRW metric, there's an a of t squared factor sitting there. Okay, so we have to bear that in mind. And so from this, we can write dx as C dt over A. Okay, well, plus or minus, depending on whether the light is coming towards you or away from you. I guess I can include that. And then there's an integral over the path. So you need to integrate from here to here. It was emitted, and then it reaches us. Okay. So that is just what I'm calling X. And then the right-hand side, you want to integrate from the time of emission to when it receives us, which is today, T0. Okay. And we would normally just say, oh, that's the time we don't have to always write the subscript emit, right? So that's the time, and maybe these T's are dummy variables. We have this formula. Are there questions about that? All right, so if you, yeah. Oh, so that you're talking about an effect on the very small scales right near the star. And in a sense, that factor is incorporated in what I call L. So imagine you have a supernova that's nearby, okay, hopefully not too close, but somewhat nearby. It will have a luminosity, which is the energy that it emits once it, say, gets through that well. Let's call that the luminosity, the final luminosity once it has done that. So I'll call that L. Now I just want to compare that supernovae to one that's much further away. And they will have the same L because they're both going to have that same redshift factor as they go out of this well that you're referring to. Okay, so then I just want to compare supernovae at distant cosmological distances. And the point is the distant ones just look very faint. That's what this formula is telling us. So it's a bit awkward, but if you take this, if I would be super explicit and plug it in there, the flux, put all this together, is L 4 pi, and then I guess I'm supposed to write x squared, which is this thing. Okay, you plug that into here. If I'm super explicit about it, I would write it out. Integral t to t naught dt prime a of t prime squared. Okay. So it's this kind of ugly looking formula, but it furnishes a relationship, you see, between the thing you measure, which is F, the flux of photons, and the time t at which the light was emitted, the time at which, say, the supernovae went off. Okay? So it's not the nicest formula, but it is a relation between F and T. Okay? So what you then do is you might have A here on this axis, which is essentially a rescaling of redshift, and flux. This would be the raw data that you get, okay, with some error bars. Something like this, you get a bunch of data points. And I guess qualitatively, let's see if I did it right, it should look something like that. Okay, it's monotonically increasing. So things that have high flux, supernovae that if the flux is big, that means they're nearby supernovae. That means it happened recently. That means it happened when the scale factor was nearly today's value of 1. So this might be, say, A of 0.9. And then these supernovae, they're very dim. They have a very low flux. That means they happen in the distant past when the scale factor was very small. So these are the kinds of, but these are just raw data that you can measure. And then with a bit of analysis, you can imagine carrying out this and connecting it to T. And so it's kind of a rescaling of this axis to then convert that data, my blue data, into what I've written as the red data points here. So you have to somehow rescale the horizontal axis according to this funny formula. Is that all right? It's a little involved because you see this formula involves A of T. And we're trying to test A of T. So to do it, you pick an A of T, you do a rescaling, but there's no guarantee that it will then land on your choice of A of T. That's not how it works. It's a much more involved business than that. Okay? But you pick your curve, do the rescaling, and then see what you get if you want to convert it back to this picture. Okay? Most people would probably go the other way and just leave it in terms of this. But to compare to a model A of t, you need to connect back to this picture. Is that all right? But if you Google these measurements, you'll find pictures of that. It's hard to find this. This is a bit involved because of all these integrals and stuff. All right, so questions about this? Okay. This is your theorist's impression of what observationless do. This is not as detailed as one could imagine. All right, so let's say something then about what one finds in terms of the result. And we're picking here just a class of dark energy models where they're characterized by a fixed W. You could imagine dark energy doing something different than that. It doesn't have to be a W that's fixed for all time. Maybe the W evolves. So this is not the most general analysis. Okay, but if we assume, like I've been doing in those plots over there, W dark energy is constant in time, then the observations give something like -1 with some error bars, maybe like a few percent level, maybe 3% or so, depending on who you ask, depending on which analysis. So in other words, once you do this analysis, the red curve that I drew here, which I kind of followed the W -1 line, is kind of the way it plays out. Okay. Okay, so it looks like this is what's going on. W is -1. Maybe it's not exactly -1, but let's work under the assumption for the rest of the class that it literally is -1. And we'll see how we might understand that. So is everyone comfortable with that? All right. So in other words, data favors what I call vacuum energy. That dark energy is the vacuum energy. All right, so now let's talk a bit more about that. So what is vacuum energy? So there are different ways of introducing this idea. And one funny way of introducing it that I can think of is to think about something that you may or may not expect me to mention right now, but is to consider the Higgs potential in the standard model. Who's seen a picture of the Higgs potential? Anyone not seen it? Mexican hat potentials. Does that sound familiar? Okay. Well, if you haven't seen it, it's okay. But it's some kind of Mexican hat. Somehow controls the dynamics of electroweak physics. And so anyway, it's a well-established thing. It's real. It's not some speculation. And gives us if you're not familiar with thinking about vacuum energy, maybe gives us a useful way of entering into the subject. All right. So there's some potential energy, and importantly, it's a potential energy density. And if the Higgs is H, the formula is just some polynomial in H. The Higgs is H, that's the Higgs field. Okay? And there's a prefactor which happens to be negative. And then there's a quartic term, and the prefactor These mu's and lambdas are just constants. Okay, and then I'll add a constant as well. I don't know, gamma. Okay, so mu, lambda, gamma are just constants. Okay, they're constants in the same way like the electron mass is a constant. They're parameters of the theory, microscopic parameters, which cannot depend on space or time. The mu and the lambda are ones that actually we've more or less met. So mu is something like 250 GeV, and it sets the electroweak scale. And lambda is something like 0.1, and there's some combination of mu and lambda that sets the Higgs mass. MH is maybe √2 lambda times mu, something like that. So if that, my 2 is probably wrong. Let's just write twiddle. But you can imagine going from 250 down to 125, and there's some square root lambda that does the conversion. But in any case, we kind of know these numbers. And gamma, see, is just a constant in some quartic polynomial, and that we don't know, and that I'm going to come back to discuss. So let's just draw a picture of this thing. So here's this potential energy density function versus the Higgs, H. And you just see, you know, when people talk about Mexican hat potentials, they imagine there's multiple axes. So there's like, I don't know, H1 and H2, and you have to draw some potential that's symmetric as you move between H1 and H2. Okay, but I'm not going to draw that. I'll just draw a 1D slice of this thing, if that's okay. One-dimensional slice. So we draw this thing, and we could get, and look maybe something like this. V versus H. And, you know, in the standard model, it matters that it has this funny shape, because in some sense we sit, well, literally you could say we sit here. You could say we sit there or there. It doesn't actually matter. But our universe tries to sit at the lowest energy configuration when you're in the vacuum. So we're somehow sitting out here, and we're not sitting at zero if this thing had a more boring shape. And the long story, but by sitting here, the particle masses, like the electron mass, is proportional to this distance here. So that's how the electron gets a mass, to say it kind of very roughly, and so on. But anyway, it's important that we're sitting there. So that's where we are today. We're sitting in the vacuum. We're sitting in the potential well. All right, but actually, I can't just draw that necessarily, because I know mu, I know lambda, I don't know gamma. So if I don't know gamma, I don't know how high to push this potential up or down. Okay, so this is just one possibility depending on gamma. So in fact, this is what you get if gamma is less than mu to the 4 over 4 lambda. It has the property that its minima are negative. You can easily check. Okay. Does that make sense? So we'll call that, I don't know, scenario 1. And you can imagine there's 2 other scenarios. So you could imagine it looks like this. The minima are positive. If I call that scenario 2, that's when gamma is greater than mu to the 4 over 4 lambda. And then you could finally imagine something very special happening where the minima touches 0. And this is when gamma is exactly equal to mu to the 4 over 4 lambda. Call that scenario number 3. Okay, so qualitatively, these are the 3 options if you don't know the value of gamma. Okay, you can see if gamma was 0, you know, this thing just starts going down, right? I mean, Just to clarify the point. Let's say gamma were literally 0, then the potential function, I hope you can see, just goes down. So small gamma, in fact, the general rule is gamma less than that number will have minima that are negative. Okay. Now, in every way, shape, and form, this displacement here from 0, whether it's this gap in scenario, what I call scenario 2, or this gap here in what I call scenario 1, is in every way, shape, or form the vacuum energy density. So if you compute the minimum of this thing, what is its value? V min. Oh my God. Spam risk. Okay. V min is just minus mu to the 4 over 4 lambda plus gamma. You can see how those statements are therefore correct. And that's just the minimum, this height here. That's right. Yeah, yeah. This is the, yeah, very good. So let me, that was the next point. Yes. So notice I mentioned that mu and lambda are measured from the lab, from colliders, but gamma equals, we don't know, because as you say, a constant normally doesn't do anything. So whether you pay attention to this constant or not doesn't do anything in lab physics, because we usually just care about energy differences. Energy differences are the things that matter. But where we're going with this, I mean, first of all, you could imagine that a priori, depending on the gamma you come up with, there's no, like say, if you, for example, if you just said, forget gamma, I don't like gamma, where does that come from? Well, then you would draw this picture. So in what I call V min, you would be telling me that V min is minus mu to the 4 over 4 lambda. You'd be just saying, I declare that to be the case. Okay? But probably just by eye, you could see that this particular choice for the shape of this thing is no more a priori, is no deeper, no more fundamental a priori than any of these other pictures. Okay? Like, why should we be paying attention to that? Okay? So in other words, gamma is just as, a non-zero gamma is just as justifiable as gamma equals to 0. In fact, you might even say it's more justifiable, because why should you pick this very special number gamma equals to 0? Or this case here is the case in which the minimum happens to be at 0, where gamma happens to be that very special number. Now, in any case, you could say, yeah, but who cares, because it doesn't do anything. But it does something when you turn on gravity. That's the point. And gravity responds to the whole potential, responds to wherever you sit, because it's the source of gravity is energy density. Right? On the right-hand side of the Friedmann equation, we have energy density. So if you tell me that you're sitting, right, you can sit here, or you can sit here, or you could sit down here, whatever choice of gamma you make, that's going to have a huge consequence for gravity, for the expansion of the universe. Right? Because we just write down h squared is 8 pi g over 3 rho. And this would be the minimum value for rho. This is an energy density. So if you're just sitting at the minimum, you're not doing anything. There's no kinetic energy, if you like. It's all just kind of potential. So your potential energy density, it makes a massive difference to how the universe expands, whether you're here or here or here or there. Okay. I might add, by the way, that this scenario here looks or that one looks a little funny, because if it's negative, you might say this equation is bad, right? So down here is also what I call this equals. I'm calling this rho vacuum. Okay? In every way, shape, or form, the vacuum energy. You're literally sitting in the vacuum. So there's no question why, it should be clear why I call it the vacuum energy. Is that all right? So you clear out everything, and you're still stuck at some point in the potential. You can't get rid of it. It's just there, present throughout the vacuum. But just as a side comment, because we're not going to actually focus on it much, but if the minimum here, and therefore rho v, were negative, that equation looks a bit dodgy because there'll be negative equals a positive quantity. You see, by the Friedmann equation, this h squared is clearly positive. But that's actually related to the fact that we've ignored curvature. So if we would be more general, we could go back and include curvature. And if you had hyperbolic curvature, so k were negative, this term would be positive, and it could compensate for the fact that that is negative, so the whole thing is positive. And that's just a side comment, okay? I say it's a side comment because there's no evidence that this guy is negative. We think rho v, the dark energy, is positive, so we're considering this kind of scenario, not this scenario. But just to make the point that a priori, conceptually, you could a priori have this or this. Okay, and just curvature will make the equations come out. You won't get any complex numbers or any weird thing going on. That part's not actually the issue. Is that all right? Okay, so yeah, this is the thing. Gravity responds to the absolute value of energy in some sense, while standard physics, non-gravitational physics does not. Okay. I could even state it just another way as to, I hope I've convinced you that if we sit here, if this is the actual Higgs potential of our universe, and we're sitting there, that height is rho v. Is everyone cool with that statement? The lowest energy, and it's stuck for all time. And if we wanted to be absolutely certain that I should call that W of -1, there are different ways you can be certain that I should also say it's -1. Okay, one way you can be sure of that. Let's write it. Let's remember this formula. So you see rho v is clearly a constant, right? In time and space. Constant in time and space, because it's determined by fundamental constants, right? These are just related somehow to the electroweak scale and the Higgs mass, and some other constant that we don't a priori know, but they're all constants. If they were explicit functions of space-time, you would have explicitly broken space-time translation symmetry, which we're not in the business of doing at this point. We're just doing standard physics. So it's constant in space-time, so that's exactly what vacuum energy density does. And if you even wanted to go a little further, you could remember rho dot is -3h rho plus pressure. Okay, and then the only way that rho dot is 0, so therefore rho dot equals 0, if and only if pressure is minus rho, so that you kill the right-hand side. Okay, W equals -1. So if I put in the vacuum, so the vacuum pressure, therefore, must obey this rule. That's one way of seeing it. We can see it from another point of view, perhaps later if there's time. There's also another way of thinking about vacuum energy. Which is actually, funnily enough, the more common way that people introduce it, is to start by thinking about quantum effects of the vacuum. So you could think of this as like classical field theory. Okay, so classically, I'm just allowed to have a vacuum energy, this or this, there. Well, that one has no vacuum energy. But the point I want to say by this picture is that maybe you'll come with me and think that suppose you were to just guess, suppose you didn't have any data, you hadn't looked at a distant supernova or anything, and you didn't know what the vacuum energy was. In other words, you didn't know if the universe is accelerating or decelerating or whatever. Okay? But given this picture, what might you guess is the rho vacuum, which is the minimum of this thing? Okay? If it was me, I would not guess it was scenario number 3. You see? Because scenario 3 is the point at which there's a parameter that I called gamma, which is exactly related to 2 other parameters in the theory by some special formula. So that some conspiracy happened that the minimum is 0. Okay? So we've never seen that in the standard model, right? A relationship between parameters in the Lagrangian, some funky relation like that, we've never seen, right? That'd be like saying, oh, imagine, I don't know, the muon's mass was the geometric mean of the electron and the tau's mass. Imagine you discovered that experimentally. You'll say, gee whiz, that's pretty amazing. Okay, that would be the analog of some formula like that. There are 3 a priori independent parameters, and they're related by some funny relation. Okay? So we haven't seen that. And so there's not a good, that I'm aware of, a priori reason to expect this and to expect that. So you might guess if you were locked in a room and you didn't have any observations, maybe this and this are more likely to occur. Just some random gamma that doesn't take on that specific value. Okay. So maybe this has like a 50% shot at being correct, and that's a 50% shot, and that's like 0.001 unusual situation. And we'll come back to that in a minute. Okay. There's a quantum point of view. Which is somehow the more common starting point on this subject, which is again to estimate what might be the energy or energy density of the vacuum. Okay. We say energy, we wouldn't say energy, right? Because if the universe is infinite, the energy would just be infinity. So you want to think about energy densities. A quantum point of view is to imagine that in the vacuum, right, somehow there are like, I don't know, E plus E minus pairs, if, for example, jumping in and out of the vacuum, or any particle that you like. And there's some energy associated with that, okay, as they sort of jump in and out of the vacuum. In the language of fields, that calculation is equivalent to saying that there are quantum fields in the vacuum, and those fields are unable to just be stuck at, if the field is called psi for the electron or something, psi is unable to just be stuck at 0. If it was stuck at 0, you would know the value of the field and its derivative, psi dot would be also 0. So that would violate the uncertainty principle. So somehow the popping in and out of particles, on the one hand, is related to fields having some sort of motion, so to speak, in the vacuum. Okay, so there's a formula for the energy of that, and which is the good old formula for the harmonic oscillator. Right? The ground state energy of the harmonic oscillator is 1/2 h bar omega. We're all comfortable with that. So if you have some, in the field language, you have some wave and it has a frequency omega, the minimum energy that that wave can have is this number, 1/2 h bar omega by the uncertainty principle. Okay? And then you have to say, yeah, but what omega do I pick? Okay, so now, if there's, say, a box, this is a chunk of the vacuum. There are waves that you can fit in the box. You can have short wavelength modes, long wavelength modes. And they have different frequencies associated with them. Okay, so there's some wave number k here, right? K is just 2 pi of a wavelength, as usual. The frequency here, I should put a little k subscript on it, in a relativistic theory is k squared plus m squared. Again, I set h bar and c equal to 1. Is that all right? That's just like writing E equals root p squared plus m squared. But in the language of waves, it's just omega is root k squared plus m squared. All right? And so I have to sum over all possible wave numbers. Okay, so each mode in the free theory behaves independently, and they each have an uncertainty principle for each wave. And so that's the 1/2 h bar omega, and then I have to consider all possible modes and sum. So it's something like this. Okay, so this is the energy of the vacuum. I haven't added any extra particles on top of this. I haven't added extra electrons or anything to the vacuum. It's just the intrinsic nature of the vacuum that in this language has this going on. All right, now this formula here, we don't like doing a big sum. You can convert a sum to an integral. A very good approximation if it's a big box. Okay? So the allowed wave numbers are very closely stacked. There's a very small difference in the k's. And when you have that scenario, you can replace a sum by an integral. So this becomes integral d3k 2 pi cubed 1/2 h bar omega. Oh, I said h bar equal to 1, but okay, there's an h bar just to remind you of the origin of this thing. And then there's a volume. That's the volume of this region, which sets the measure on the integral. Okay, you may have, I don't know how many of you have seen that before, but when you convert a sum over k to an integral, this is the appropriate measure. Okay. So that's very nice, because if you take right? The volume of the universe to infinity, you say you get infinity, that's fine, but I care about the energy density. And so I just divide both sides by V. Okay, so this tells us rho vacuum. Or I could say this is the quantum correction. There was my classical thing from the Higgs potential and the way I've introduced things. Think of this as a correction to that. Is that all right? I could write delta V, delta correction. This is therefore divide by V, E vacuum over volume. So it's just this integral. I'll set H bar to 1 now, omega K. But let's be explicit. So omega K is this root K squared plus M squared. Right. And then we should do this for every species of particle that we have. The particles have different masses, right? And so if I label it I, for the different species, say the electron, and then you've got to do the W boson and so on and so forth, you should sum over all of them. They'll all contribute. Sum over I, the species. And then there's another little subtlety, if we bother, which is that these formulas I wrote down for you are correct for bosons, but there's actually a minus sign if you did this for a fermion. So there's also some plus minus for bosons and fermions. You've got to include that in the summation. But in any case, you get some formula like this. Now, the K, right? You can't put in an arbitrarily small K that fits in the box, but it seems like you can fit in an arbitrarily big K, right? As you go to higher and higher K, that just means you're fitting in tinier and tinier wavelengths, something like this. Okay, so there seems to be no problem to do that. And that famously means that this is actually a very horrible integral, you see, because if I try to integrate K out to infinity, this is just going to give me infinity. Right? This diverges like K. Right? High K, the integrand is K, and then you integrate over all K out to infinity. So this is a horrible divergence. Is that all right? Okay. So the long story as to what on earth you would do with this, and you could even say that it's not even completely settled in the literature as to the right way to think about this particular divergence. But in some sense, there's a procedure of renormalization. I just give you a flavor for it, which somehow deletes the infinities, again, in a way that's not properly understood in this context. But if you blindly do that, you'll get a nice finite answer, which happens to be m to the 4 over 32 pi squared. And there's some log correction. I don't know, MR. There's some renormalization scale. The details don't matter for us. Okay, it's inside of a log, so that's not going to affect our thinking much. Okay, so anyway, this is some estimate for the vacuum energy density. Yeah, I mean, that's equivalent to just declaring that integral equals 0, which is even stronger than what I'm doing. Okay, so you have something like this. And now you could imagine doing the sums over the W's and the Z's and the top quarks and so on. Well, let's now compare all this to the observed value. Okay, so both my classical contribution here, which I gave you this formula for it, and even a quantum correction, this. This formula, by the way, is only a first estimate because this is at the level of free particles. The particles are really interacting. If you try to compute the vacuum energy of that, it's a complete nightmare. No one really knows how to do it. So for example, in QCD, the vacuum is a horrible thing of quarks and gluons interacting in some way. I can't hand you a neat formula for that like this, but people can try to estimate it or compute it on the lattice. But this is just a first estimate. Okay, anyway, let's now talk about the compare these estimates to the observed value. Oh, okay. So there's that's a technical point that I didn't explain, but there's a scale at which you perform the renormalization. When you do renormalization, you have to pick some scale at which you define things. For example, the scale at which you define the masses and so on. Okay, in a QFT course, we'll get into that. But for now, I don't want you to pay too much attention to it. It's inside the argument for the log. It's not going to affect our thinking too much. If you want to treat the log as 1, that'll be good enough for this. But what we're about to see is the disaster of these formulas, however you cut it. Is that all right? So let's have a look at the values of these things. Okay. So let's look at, again, the Higgs potential, sort of the classical version I gave you. So remember mu, we know there's a couple of things we do know. It's 250 GeV, and lambda is like 0.1. So then, if you go back to this estimate, let's first look at the first term here. Let's recall rho vacuum was estimated as minus mu to the 4 plus this gamma. And the minus mu to the 4 over 4 lambda, then you just put in these numbers. And this is something like minus 10 to the 46 electron volts to the 4. Okay, because you see there's the GeV, but now I'm going to electron volts, so there's a big factor. But you recall, I told you the value of the vacuum energy we've measured in the universe. It's driving the current acceleration. So let's say rho vacuum observation is about 2.5 times 10 to the minus 11 electron volts to the 4. Okay? So they're off by, in this estimate, 57 orders of magnitude. Okay? That piece is 57 orders of magnitude, then the final thing. So in this language, let's say you put aside the quantum correction for a moment. We'll see if that helps. Where in scenario 2 here, right, we have a positive vacuum energy. That's some positive number, 2.5 times 10 to the minus 11. But we're incredibly close actually to scenario 3, just slightly off, right? So you could imagine this is not an inconsistency. These two facts are consistent. If I come here and I say, all right, you know, if I imagine that gamma, let's write this out. Rho v is something like minus 10 to the 46 eV to the 4. That's that term. And then there's a gamma. But let's imagine that gamma happens to be the value 10 to the 46 eV to the 4 times, so this is gamma, 1.00025. You see? Where the number of O's here is, I guess, 56, something like that, 56 zeros. You get what I'm saying? Right? You can imagine that these two terms cancel to ludicrous precision. And so that you don't have exactly this formula. You have gamma equals that, but then times 1.025. Okay? And then you would raise the minimum up ever so slightly to the observed value. So that's how vacuum energy would work. If you ask about the quantum corrections to these things, if you say, well, maybe, I don't know, maybe that's just 0. Maybe we should just live in scenario 3 for some reason. Maybe the quantum correction is that little thing that jumps us up to the 2.5 times 10 to the minus 11. Well, that doesn't work out at all well, right? So if you take, say, m top to be something like 170 GeV, you know, mz is 90, I don't know, 91 or something GeV. You see, you're also talking about things on the ballpark of 100 GeV to the 4. Okay, so it's like 10 to the 11 to the 4 again. So there's some 10 to the 44 here. Now there's some pi's, whatever, that doesn't help us too much. So if you do this, you'll get delta rho v is something like, I think you get 10 to the 41 or something, EV to the 4. It's a little bit smaller, but it's still ridiculously bigger than the observed value. Okay? People don't really spend too much time actually carrying out the sum and worrying about the plus and minus because it's just insanely wrong. Okay? And it's also sensitive, therefore, to other particles we don't even know about. Right? If there are particles beyond the standard model that are even heavier, they're going to be even more important to the sum because there's an m to the 4 there. Okay. But in any case, any hope that say the masses in the standard model allowed this summation to come out to be 2.5 times 10 to the minus 11 instead of the typical value, 10 to the 41, which is what, say, the top quark will give you. There's no hint whatsoever that there's some amazing cancellation that has taken place. Okay. So the short of it is no one really knows what to do with it, but it is to say that vacuum energy, right? Like had our universe looked like, say, this, where the height here is, say, comparable to that height, that would be the scenario where there's no magical cancellations. It'd just be some gamma, some random number. Or this scenario. This would just be, okay, sort of boring scenario as far as just from the point of view of particle physics. It would not be a boring scenario for us because if the height here was, say, order 10 to the 46 instead of 10 to the minus 11 in units of EV to the 4, right? That means rho would be 57 orders of magnitude bigger, right? And that means that Hubble, because of a square root, would be 28.5 orders of magnitude bigger. Does that make sense? So if these estimates were correct, Hubble would be some 28 or whatever orders of magnitude bigger. And that means this room would have ripped itself apart in like a nanosecond or something, okay? So from that point of view, of course we cannot be living, I shouldn't have this here, this person's dead, okay? This person's dead, that person's dead. This universe collapses in a nanosecond. And that person's happily alive. And if you raise it up to 10 to the minus 11, imagine the height there is 10 to the minus 11. I'm not going to try to draw that. They're happily alive as well. Okay. So anyway, at the end of the day, no one really knows what to do about this. Okay. And actually mumbling about who's alive and dead is actually the best we have at this point. Some people say, well, we're there because of that reason. To exist in universes where there are observers to observe those freak occurrences where there are these insane cancellations. And there are no observers in these universes where the freak cancellations didn't occur. That crummy argument is actually the best anyone has come up with so far. So just to put it that way. And people have thought about this for a long time. All right. So maybe, any questions about all this? Yeah.
Like a sum for all of the possible like energy fluctuations like happening in the vacuum.
Oh, for this quantum one?
Yeah. Like all the levels for
That's right, yeah.
I can see
Yeah. Yeah.
I think high energy fluctuations are less likely than low energy fluctuations. Like,
That's right.
it just doesn't seem like physical that, 10 TeV cosmic rays going to suddenly pop into existence out of the vacuum. But it seems like we're including those kinds of things in this.
Yeah, so this integral is written here. Right, so then there's this issue, as I said, this thing diverges. And there's it's not properly understood what to do about that. Now, in a way, what I'm doing, where I just said the word renormalization, is I've deleted all the high energy ones in a way. So the only ones that remain are the ones associated with the known masses. Okay. So this is a one that's harder to delete in a consistent way, even though you said the word normal ordering, especially when you have interactions. Even the normal ordering doesn't kill everything when you have normal ordering. So the really high energy stuff, there's another point of view on this, where they don't do this normalization stuff. They do something maybe a little bit more along the lines of what you're suggesting, is you just go up to some K, I don't know, K max, let's call it. You keep on going and you say beyond that, what you would say is that there's some new physics that changes the integral. Because the rules of quantum field theory, if you like, say I should just do this integral. But you could cut it off by saying there's a point at which I don't trust this analysis anymore. It's kind of an extreme thing to say because it's kind of the point at which the you have to say quantum field theory is breaking down. That's like some UV cutoff. There's a very extreme type of UV cutoff. It's not a standard UV cutoff. Now, some people would estimate that that cutoff is something like the Planck scale. Okay, I mean, that's not guaranteed to be true. But if you estimate, for example, this to be the Planck scale, the Planck mass is something like, or what's called the reduced Planck mass is on the order of 10 to the 18 GeV. Okay. So if you open up your typical book or Google this, that's actually the most common estimate that people write down. Let's put aside the 2 pi's and so on. This is then on the order of m Planck to the 4. So never mind top mass to the 4. People estimate the Planck mass to the 4. Okay, then this is many orders of magnitude bigger than even my estimate. And then this one is actually 120 orders of magnitude bigger than the observed one. So then you would say there's cancellations at that level of precision. So that's the most conventional actually point of view on this. I mean, but yeah, what to do with the upper endpoint is actually quite subtle and not properly understood. Just deleting QFT gives you this. There's a kind of a point of view where you allow QFT to be valid to all energies, and you have to go through this renormalization procedure. But the mass terms are things that we don't quite know how to delete in a consistent way. Yeah.
Value and like reverse engineer the mass, and like what would you get for an estimate of that mass? Like I assume it would have to be a really tiny value.
Oh, if you just said, yeah, if there was just one, let's say, type of particle in the universe. So you have to be in a scenario where you don't have all this other stuff. There are no W's, there are no Z's. Even the electron is like 30 orders of magnitude too big. So, but yeah, if you just say what m such that it matches, that's right. Yeah, you basically take 10 to the minus 11, take its 4th root, put in some pi's. So I think it's like EV or something. Yeah, that's a good question. So m, if m was like 10 to the minus 3 EV or something, you can just see, you take the 4th root and put in some pi's. There's some number there that this would spit out the right value. Some people fantasize along those lines, but it looks to be even a little smaller than neutrino mass. But that's right. But there's all this other junk that just overwhelms it. So we don't know how to keep that. Even if tomorrow someone discovers a particle with that mass, or if someone discovered a particle with the mass such that when you put in all the pi's and everything came out to the exact same value, that would be very interesting. But people would still scratch their head and say, why did nature focus on that bit and delete all the other stuff? That would still be a big mystery, but it would be a clue as to what was going on. Okay. So in any case, there are many, many things that try to generate a big vacuum energy. And the concept, the a priori concept of a vacuum energy is a very reasonable concept. There's nothing screwy to expect it. And the problem is that we expect it so much that we're confused by the fact that there's so little of it in the universe. So that's the theorist's perspective. There's so little vacuum energy rather than a huge amount. And the fantasy amongst some people is that for some unknown reason, nature wants it to be 0 and there's a little bit left over due to something else that's not vacuum energy. There are people who write papers in this direction. But no one knows how to get this thing to be 0 as a starting point. And then maybe the true dark energy is something else, like W of minus 0.95 or something that might fit the data, and that thing is not quite vacuum energy anymore. So we don't know what to do about that. Maybe I have just 2 minutes to also say, since I haven't said the word cosmological constant in this class, even though I probably should. So Einstein called what I call the vacuum energy a cosmological constant. And there are different ways of introducing that, but let me just state, if you start from an action, so there's an action for gravity. This is the Ricci scalar that we talked about some lectures ago. This is just the standard model Lagrangian, which I'm just writing L. Okay. And then what you can do is you're allowed, and I'll call it capital lambda, you're just allowed to include a constant a priori. There's nothing wrong with including a constant. Okay. You might say that there's a constant lurking in here. In some sense, that's the language I've been dealing with, speaking in. There's somehow a contribution from the Higgs potential is inside of that, for example. But we could even flesh it out and say there's an overall constant here. When you don't say the word gravity, this constant does nothing, because a constant in a Lagrangian or an action doesn't do anything. But gravity, what we call a constant, is a constant in space and time. It still multiplies the root g here, the natural measure on integration. Okay? And so it's not, it's dynamical now. It's a constant, like the electron mass is a constant, but multiplied by something that depends on on the fluctuations in space-time. And so then when you vary the action to get the equations of motion, let me just tell you what you get. You'll get Einstein's equations. I'll write one up, one down. This is the contribution from the standard model. That term gives you this. That term gives you this. And then this term gives you lambda times Kronecker delta mu nu. This is just what you get if you were to vary the action. I'm not going through that here. And that combination that you get from varying this thing, that combination is exactly the way a vacuum energy appears. Right? So this is like a contribution to T mu nu, right? This bit here is lambda delta mu nu. So it's just lambda, 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 bunch of zeros. Okay? And you recall that we wrote energy density of some species as rho minus pressure, minus pressure, minus pressure. Right? That was the T mu nu for regular stuff. And so this predicts the values of rho and p to be rho is lambda and p is minus lambda. In other words, exactly the properties of vacuum energy as I've described, W equals -1. So that thing there is sometimes called the Cosmology constant, but it manifests itself indistinguishable from just calling it vacuum energy. I could call it rho v if I wanted to. All right, so I just wanted to mention that. These are sort of the same thing. Einstein put his lambda, when he put on the cosmology constant, he put it on this side of the equation and thought of it as a property of space-time. Somehow we do that. You put the stuff on the left, that's a property of space-time, quote unquote. When we put it over here, we somehow think of it as vacuum, somehow a property of matter. Okay, so whether you choose to put it there or there is kind of a psychological difference. But I remember going to a colloquium a few years ago by Rocky Kolb, where he joked that in the last 100 years, our development in our understanding of gravity has been to move a term from one side of the equation to the other. And that's about it. All right, so maybe we'll leave it there for today.